Hello everyone. We are going to be working on a new section. It's 7.5, Exponential and Logarithmic Equations and Inequalities. We're really going to take most of our focus on equations, but we will introduce the idea of an inequality here. So let's begin. An exponential equation, so let's go ahead and fill that in. An exponential equation is an equation containing one or more expressions that have a variable as an exponent. So when we solve exponential equations, we want to try writing them so that the bases are the same. So we want the same bases. I like to look at these as common sense properties. I think if we look at them, we really thought about it, we would say, oh, we already knew that. If I have a base b to the power of x, and it's equal to base b to the power of y, if my bases are equal, then my powers must be equal. So if this is true, then x must equal y. We have a couple of limitations. B cannot be 0 or 1. 0 to the 0, first of all, is undefined. And 0 to any power, 0 to 1 is 0, 0 to 2 is 0, so that would break the rule. B, the base can't be 1, because 1 to any power is always going to be 1. So these are two stipulations that we cannot have as a base. And that's simply because it breaks the rule. Because if we have 1 or 0 as a base, then x does not have to equal y. All right, the logarithmic side of the rule, if we talk about the logarithms, so same bases, the powers must be equal. If a is equal to b, and I take the log of this side, then I must take the log of that side, and they're still equal to each other. We actually used this idea when we did our change of base. So instead of just using the change of base formula or property, we went ahead and say, hey, we'll just come in and take the log base 10, log base 10. If these are equal and I take the log of each side, then they're equivalent. So if I have log a equals log b, same base, then a must be equal to b, or I can take the log of both sides. Stipulations here, a and b both have to be greater than equal to 0. I'm going to star that because that is an important fact, and that's going to come up for us later. So again, a has to be greater than 0, b has to be greater than 0. You're going to know that we never take the log of a negative number. We never take the log of 0, and so that's an important rule. All right, so again, I don't think if you've been working with logs that this is one of the hard problems. I think these are easier ones, and there's lots of ways you can do this. So we're going to start using an easy method by playing with the bases. And I just want to remind you that both of these properties are more properties of logarithms that you should know. That way when they come up, you know the rules to use. So we have some explanation here to help guide us on these first examples. I have 8 to the x, and that's equal to 2 to the x plus 6. Now, if I really wanted to, I have unknown exponents, I could jump in and take the log of each side. And I can solve it that way. No problem. Take the log, bring the x out as multiplication, take the log, bring x plus 6 out as multiplication using my power property, and then we could solve it algebraically. What we're going to do is rewrite each side with the same base. That's what we're going for, is that same base, and we're going to have a power of 2. So 2 to the third is the same as 8. So I'm replacing with my 8 with 2 to the third to the power of x, and that equals 2 to the x plus 6. So there you have it, right here. Here's what we're looking for. They both have the same base of 2, so that means that this power must equal this power. And if we're using our power properties, it was 2 to the third is 8 to the power of x. Power to power we multiply. So I really have 3x is equal to the power over here, which is x plus 6. So again, this 2 to the 3x is the same as 2 to the 3 times x. And that equaled 2 to the x plus 6. All right, and then I have a simple algebra problem to solve. So all I have to do is move this x over by taking the opposite. I get 2x equals 6, and divide out by 2, and x equals 3. So we have found the answer. If I want to check that answer, I'm going to take my calculator, and I hope you can see this a little bit, and I'm just going to plug it in. I'm going to plug in 8 to the power of 3, and I get out 512. I'm going back to the very original. I'm also going to plug in 2, and the reason I wanted to show you this is I wanted to remind you that you need the parentheses, 3 plus 6. Or you can just simply put in 9. but you need the parentheses to get that power. If we did it as 2 to the 3 plus 6, your calculator is going to take 2 to the third, which we know is 8, and then add 6, and we get out 14. So you want to make sure that you enter it using parentheses or just simplify your power to one number. Okay, it's as simple as that. Again, if I couldn't change this base, I would come in and take the log of each side. So in part B, the first thing I wanted to try to do is I have a base of 5. I wanted to try to make 200 a base of 5. So I was looking at some numbers, and I know that 5 squared is 25, and I know that 5 to the third is 125. So I'm going to go ahead and try 5 to the fourth, and I'm going to find that it is 625. So it's too big. I know the power, 5 to the power of 3 to 4. Somewhere between 3 and 4 is going to get me that 200. And since 5 to the third is 125, I'm going to be closer to that power of 3. So I cannot get 5 to a nice power to get 200. So I'm not going to use a base of 5. I'm going to take the log of both sides. So I'm going to use that second property for this one. So I'm going to come in and take the log of 5 to the x minus 2 and keep that equal to the log of 200. All right, so using my power property, I'm taking the log of something to the power, so that power is going to come out front. And I think it's really important here that I address this by putting it in parentheses, because that does affect us other problems. So it's all of this, x minus 2 times log 5 equals log 200. And then if you did the change of base lesson with me, we're not doing anything new here. I want to solve for this, x minus 2. So the first thing I'm going to do is I'm going to get rid of that times log 5 to break this out of the parentheses. And so I end up with x minus 2, and I'm going to put an approximate symbol here. Okay, and I'm going to go ahead and divide the log of 200, close my parenthesis, that's really important, divided by the log of 5. And I'm going to close my parenthesis again, and I end up with 3.292. So I'll keep a couple decimals there. 3.292, and I just have one more step to finish this problem, and that is to add the 2 over, and so I get that x is approximately 5.292. Now, the next thing again is I would go up and I'd put this in the calculator, 5 to the power of parentheses 5.292 minus 2, and I get that, really I'd get that 3.99 or 92, and I get 199.99, which is really close to 200. Okay, so we have a couple more problems just to practice what we're doing. So the first thing I'm going to look at is I'm going to see that I have a base of 3. Can I turn 27 into something with a base of 3? Well, we already know 3 squared is 9, so let's try 3 to the third. Boom, it's 27. So I'm going to rewrite this as 3 to the 2x equals 3 to the third, because 3 to the third is 27. So this is like the shortcut. If I can make my bases match, then I can go ahead and just quickly look and say, hey, my bases are equal, so that must mean that my powers are equal. So 2x equals 3. So I'm not just getting rid of the bases, they're not canceling out, I'm not dividing them out. I'm just saying if the bases are equal, then the powers must be equal. So again, we're going up to this first property. The bases are equal, then the powers must be equal. We just had to manipulate our base, and we were able to do that, so it's a nice shortcut. So all I have to do is divide by 2, and I get x is equal to 3/2 or 1.5. Again, to check that, I'm always going to check it, especially on a graded assignment, a test, or a quiz. 3 to the power of 2 times 3/2. And again, we want to put parentheses here. I'm not sure where mine went, and that is not working out for me. So parentheses 2 times 3 fraction 2, close my parentheses, and there is our 27. Again, it's really important that you try plugging this in the calculator. That way you're clear of what to do. All right, so when I went to do this one, the first thing I try to do is say, oh, 7 times 3 is 21. I'm not multiplying by 3, guys. It's got to be 7 to a power. 7 to the first is 7, 7 to the second is 49. So there's no nice way of rewriting 21 with the base of 7. So that means I'm just going to come in and take the log of each side. I'm just going to squeeze that in there. And I'm always using log base 10. And I'm going to use my power property. This is why these properties are so important. And I get negative x times log of 7 is equal to log of 21. And again, this is why I like to show that change of base rather than the quick rule to remember, because now I know how to solve these because I've been doing it. And then I have negative x times this log, so I'm going to divide out the log. And again, it's really important that you recognize log 21 is one number, log 7 is another number. This is not a single log. So you can't cancel out the logs. You can't take the log of 3. 21 and 7 aren't reducing here. You're left with the negative x. And again, I'm going to go ahead with an approximate symbol. And we need to take the log of 21 and close those parentheses, divided by log, it's been a long day, of 7. Close those parentheses, and we get about 1.565. 1.565, and we are almost done, but I do have a negative x. So I'm going to go ahead and divide both sides by negative 1, and x is approximately negative 1.565. All right, looking at my last one, I have a base of 2. There is no base of 2 that's going to give me 15. Okay, 2 to the third is 8, 2 to the fourth is 16. So I'm going to go ahead and I'm going to jump in and I'm going to take the log of both sides. And so both practice B and C are the second property, where we have these bases set equal, so we take the log of both sides. How do I know to take the log? How do I know that that's what I have to do to solve this? I have an unknown power, and that's what logs do. Logs solve for unknown powers. Use my power property, bring that out front. So I'm going to use parentheses again. 3x times log 2 is equal to log 15. Now, if you really wanted to, we didn't need the parentheses here. We could divide both sides by 3 log 2 to leave the x alone, but I'm just going to go ahead and do this in 2 steps right now, so it's not too much or overwhelming for anyone. So we're dividing by log 2, and we're left with 3x. And again, I'm going to go ahead and throw my approximate equal to sign in there. And I'm going to take the log of 15, and I'm going to divide that by log 2. And I get about 3.907. 3.907. And I have one final step. I need to divide both sides by 3. And so x is approximately, I'm going to go ahead and take my answer and divide it by 3. It's approximately 1.302. If we took the approximation divided by 3, we get the same rounded answer, so we're good. Okay, let's continue on. We have a word problem here, an application problem. So I'll give you a second. All right, so you can choose a prize of either $20,000 or 1 penny on the first day, 2 pennies on the next day, and then so on. So it's going to double. So on the first day you get 1 penny, the next day you get 2. On the next day you get, so on the third day you would get 4 pennies, then 8 pennies. So it's doubling, which is exponential growth. So in what way would you receive more, or sorry, on what day would you receive more than the value of the car? And honestly, this is a really surprising problem. Now, we have a little bit of conversion to do, so I'm going to walk you through this quickly. We are talking in pennies for the day, but we are starting out with dollars for the car. So we're going to take our $20,000 and multiply it by 100. So we get 2 million pennies, 2 million cents. Now, on the first day, you receive 1 cent. So we're going to keep everything as pennies. We're not going to write 1 cent as 0.01. We're going to write it as 1. But we're going to kick it back. We're going to take 1 cent and rewrite it as 2 to the power of 0. Because remember, our multiplier is 2. The money each day is doubling. So we want to write that as a base of 2. So then you would receive 2 to the first on the first day, and so forth. So on that initial day, 2 to the 0, you receive 1 penny. and then the next day you get 2 to the first. It's the first day, n is the number of days, and so on. And so we have this as 2 to the n minus 1. N is the number of days, we take away 1. So we are taking this. This is the amount of money we get in pennies, okay? So this is our cents, our penny a day. And this is the car value that we've written the 2 million in scientific notation. So 2 million is 2 times 10 to the 6, because when we adjust the decimal and put it here, it has to be multiplied by 1 million, which is a 1 with 6 zeros. And so I wanted to make sure you understood. We built this equation for the penny a day, n is the number of days minus 1, and then this is simply the 2 million pennies that the car is worth. Okay, so now that we've gotten that done, I have 2 things that I need to solve. So we're going to take the log of both sides to solve for our unknown power. So come in, take the log of each side. Oh, and one of the important things is it is greater than. I could create this problem with an equal sign and then just figure out when it would be greater. We have an inequality here. We want to know when our pennies a day is going to be greater than the value of the car. So we're going to do all the same rules that we do with logarithms, with an equation, with an inequality. All right, so the first thing we did was we brought this out. The next thing I'm going to do is I'm going to rewrite my problem, and I'm going to bring my power out front. So it is in parentheses n minus 1 times log 2 is greater than. Now I want to take a second here. This is multiplication, so I'm going to break it up to addition. So this would be log base 10 of 2 plus log base 10 of 10 to the 6. So again, I'm using my property from before, where if I have multiplication, 2 times 10 to the 6 on a single log, I can write it as addition of 2 logs. Now, next thing, we have another property. This is log base 10 the whole way through this problem. And so here's another property. It would be n minus 1 times log 2 is greater than log 2 plus 6. I know, it seems crazy, but log base 10 of 10 is 1. And so that 6 comes out front. So this piece right here is 6 times log base 10 of 10, which is really 6 times 1, which is 6. And so again, we're using our property. 10 to the first is 10. That's why this outcome is 1. All right, well, now that I have that, it can seem a bit confusing because you have some stuff going on. I'm going to leave this over here, and I want to get the n minus 1 by itself. So I'm actually going to divide by log 2, which can create some problems. We're doing all this hard math, and then people make errors on the most basic fundamentals. They know better. So I have n minus 1 left over here is greater than. Ladies and gentlemen, these logs do not cancel out, okay? I have 3 terms, 1, 2, 3. These do not cancel out. So if I really want to get an accurate answer, I can leave these alone and add 1 onto the end. Otherwise, what I'm going to do is I'm going to throw this in my calculator, and I want to do it really carefully. If I wanted to do it completely in my calculator without skipping anything, I would take parentheses, and I would take log of 2, close that parenthesis, plus 6, and then close that. So now I'm saying I have the numerator. So I have log 2 plus 6 all in my numerator, and then I'm dividing by single thing of log 2, close parentheses, and I end up with this number of 20.93. Okay, so 20.93. Real quickly, the way to avoid error and not use extra parentheses would be to do your numerator first and add 6. Again, you do have to close that parenthesis on your log, but add 6 and then go ahead and divide by log 2. That way there's no chance of you missing a parenthesis. Okay, my last step is to add 1, and so I get that n is greater than 21.93. So n is greater than 21.93. Okay, so what does that mean? Well, we were trying to figure out how many days it was going to take. So on day N, you receive this much money. And so in 21.93 days, and we want to round that up. So in about 22 days, the penny offer, we'll call it, is worth more than a car. And so that is definitely something to think about. Most of us would automatically have jumped and said the $20,000 car. I could totally wait 22 days to get $20,000. No problem with that. Okay, so next idea, again, this rolls right along with what we're doing, is that we are looking at logarithmic equations, and we're going to use all of our rules. We've really been dealing more with expressions and properties. Now we're getting into solving equations with logarithms. So notice there's only a log on one side here. All right, so we are going to follow all the same rules, and we're going to follow all our properties of logarithm rules. If I have log base b of x equals log base b of y, this really, again, is a common sense rule. If my logs and bases are the same, then what I'm taking the logs of must be equal to each other. That's all it's saying. If I'm taking the log of each side with the same base, then the x has to equal the y, okay? So if we look at this, I bring that up, and then you look at this problem, and you say, well, that's not the same thing. We're going to use some properties here, okay? There are several ways to solve this. One of the first things I would think to do is say, hey, this is in logarithmic form. It doesn't help me. So I'm going to go ahead and change it to exponential form. Now, this is going against what they're telling us to do, so we'll talk about that in a minute. But I would just say, hey, base of 3 to the power of 2 is equal to x minus 5. I mean, that's how simple it is. And then we know that 3 squared is 9, and 9 is equal to x minus 5. And then I just simply add 5 to the other side. And there it is. X is equal to 14. Now, the downfall of this problem is I can't plug the 14 in here and just plug it in a calculator. But 14 minus 5 is 9. And then 9 to the second, I just messed that up. 3 to the second is 9. So it is checkable if I can change this, and I put the 14 in here, 14 minus 5. So I have 3 to the power of 2 is 9. So it does check itself out. Okay, that's how I would do it. I would say logarithmic form doesn't help me, change the base. Now, what they are talking about doing, and this is a nice quick way of doing it also, but again, it depends on what you see. I see it this way more, but you can do the change of base with making this a base of 3 and making this a base of 3. And so it's the idea that if I have 3 to this power, then I have 3 to the power of 2. If my bases are equal, my powers are equal, just like the other property on the front of this page. So if that's true, 3 log 3 cancels, and that leaves me x minus 5 equals 3 squared, which is 9, and again add 5 and x equals 14. I think this is the way most of us would see it, but I wanted to show that you can actually bring in and manipulate your base. And why did I choose a base of 3? Because my log had a base of 3, and I'm using my property that the 3 to the log base 3 would cancel. Okay, so some more examples to work on here. We have some equations, and we're definitely using our rules. Again, these notes give you some extra help to walk you through in case you're stuck. It says write as a quotient. I'm going to remind you that that's the same as writing it as a single log. Okay, so I'm going to try to move a little faster. I know this recording's getting long. Notice these are both log base 10. The downfall is I have variables, so I can't put it in the calculator. I could throw this in the calculator, move it over, and clean up, but we're going to go ahead and put it together. We're going to make this as log 45x all divided by 3 is equal to 1. So whenever I have subtraction, that leads to division in a single log. Then I'm going to take this log, and I'm going to reduce this, and I end up with log of 15x equals 1. now that I've gotten it written as a single log, again, you can use 10 as a base for both sides. So this is log base 10. So I can come in and say, well, I'll put a base of 10 on here, a base of 10 on here. 10 log 10 cancels, and it leaves me with 15x equals 10. And then I simply divide both sides by 15, and I get x equals 2/3. So I can solve it that way. Again, I think when I'm at this point, the way I see it is that log of 15x equals 1. The way I'm seeing it is I have a base of 10, 10 to the first, base is my base, 10 to the first is 15x, and you can see that we end up with the same results. So whichever way it clicks for your brain is okay to do. All right, now in this next problem, we have something a little different. We have a power up here, okay? So I could essentially make this 4 to the 7th equals x squared, and that gets a little messy. So I think what I want to do is I want to bring this out and make it 2 times log base 4 of x. Again, it's really important that you know your properties, because if I know my properties, this goes very smoothly. Again, that anytime I have a log to power, the power comes out as a product. And I'm going to go ahead and divide both sides by 2. And so now I have log base 4 of x is equal to 7/2. Okay, so with that in mind, I have a log base 4. So I'm going to change this to exponential. It's 4 to the power of 7/2 is equal to x. So my answer falls right out. So that would be 4 to the power of, and I'm going to go ahead and use parentheses. You could use 7 divided by 2, or 7 fraction 2, or 3.5, and we end up with 128. Now, why you get 128 jumps back to, this would be the square root of 4 to the 7th, so it is a pretty large number. Okay, again, other ways to do that, you could work it out the other way, and that's fine. All right, next problem. What I see here is addition. Okay, so I want to write this as a single log. Notice that x is in 2 places. I want to clean it up, put it together. If I would have a log on the other side of this problem, I'd want to bring it over. Okay, I want to put all the logs on one side and all the loose numbers on the other side. And I'm going to write this as log x times x plus 9 is equal to 1. And it's pretty important in here that you have x times x plus 9. So what we really end up with is log of x squared plus 9x is equal to 1. Okay, now this says use the inverse properties. So again, you could change this to exponential form. That's what I like. This is a base of 10, or you can come in with a base 10 and a base 10 to cancel that out. Either way, this would be 10 to the power of 1 is equal to x squared plus 9x. So whether I put a base 10 here and a base 10 here, I get the x squared plus 9x is equal to 10 to the first, or just 10. Now, the issue with this that we haven't run into is I have a quadratic now. When all the other problems I just had x, and I had to solve it by inverse operations, but now I have x squared. So I'm going to treat this as a quadratic. I'm going to go ahead and swing that 10 over and set it equal to 0, and that's going to make that a negative 10. And it's your choice how you solve this. I'm choosing to factor it because it factors, so I get 0 equals, and it'd be x plus 10 and x minus 1. And again, you want to double check yourself. And I'm going to use my, oh, there it is right there, my zero product property here. Again, if it didn't factor, or it was a harder factoring, I could use the quadratic formula, completing the square. I could graph it. I could use charts. I'm finding x when y is 0, and that's why we set it equal to 0. And that means that x could be negative 10, or x could be 1. And the issue with this is x was what I'm taking the log of. So if you're not paying attention, you would say, I'm done, I got these two answers. But this x is negative 10 is going to throw out, and x can only be 1. If you remember from our first page, we had in the rule, whenever you take the log of a number, that that number has to be greater than 0. You cannot take the log of 0. You cannot take the log of a negative. If you try to take the log of a negative, just because you were checking it, and I try to take the log of negative 10, I'm going to get a domain error. Okay? Cannot take the log of a negative number because you won't get that outcome. So x is simply 1. Okay, so we have a couple more problems to try like this. Again, I have 2 logs here and there's addition. And what I like showing you about this problem is I can't jump right in because it's not a log plus a log. It's log plus 3 times a log. So I actually want to move this up. One of the mistakes people try to divide it out, I can't do that because this doesn't have a 3 here. So I'm going to move that up and rewrite it as 3 equals log 8 plus log x to the third. Okay, so now that I have that, it's going to be 3 equals log, notice these are base 10, of 8 times x to the third. Okay, so log of 8 times x to the third, addition leads us to the single log with the multiplication here. And then I'm just going to take it out of logarithmic form. This is going to be 10 to the power of 3. Base to the power of 3 is 8x to the third. Okay, well, what is 10 to the power of 3? It's a pretty simple number. So I'm going to go ahead and write that out. 10 to the third is 1,000. So let's clean that up so we're not overwhelmed. Equals 8x to the third. And then we have to do a little algebra. I'm going to go ahead and divide both sides by 8. And yeah, you can reduce that fraction, but we're just going to throw it in the calculator real quick. And we're going to take our 1,000 and divide it by 8, and we should get 125. So 1,000 divided by 8 is 125. And then I have this x to the third. And just like if I had x squared, I would take the square root. I'm going to take the cube root of both sides. And just to remind you, when I go to throw the cube root in the calculator, if I need to, I have to define my root. So I type in my 3, I hit my second function, and then there's my any power, and you can't see that, but above it is my any power. There's my x root key. So 3x root of 125, and we end up getting 5. So x is 5. Now, since this is log base 10, I could put this in my calculator. Log 8, close those parentheses, plus 3 times log 5, close parentheses, and we get out our answer of 3. So I can always check it if it's base 10 in my calculator. Okay, now, the good news is this is set equal to 0, and the logs are on one side. The bad news is there's a 2 out front. And again, the mistake people make is they say, well, I'll just divide both sides by 2. But this is not multiplied by 2. So you would have to divide this by 2 to cancel, and then this would be stuck. So we're just going to pop that back up. These are the times we're going to put it back up in its power position because it's not helping us as the product out here. And this, I can actually do this problem 2 ways. There's a really quick shortcut for it, but I'm going to go ahead and show you this way. This would give me log of x squared divided by 4 equals 0, because my subtraction is going to give me a fraction. Again, this is a property, and the x squared is on top because we're taking away the log 4, that's on the bottom. And so here I have again a base 10. So this would be 10 to the 0 is equal to x squared over 4, and anything to the power of 0 is 1. And so I get 1 equals x squared over 4. And then I'm going to multiply both sides by 4. And I get 4 is equal to x squared. And just like before, we would jump in and take the square root. And since I'm taking the square root of a quadratic, x could actually equal positive 2 or negative 2. Remember, I'm asking you what squared gives me 4. 2 times 2, negative 2 times negative 2. But again, since I'm taking the log of x, I can't have the negative, so x can only be positive 2. Okay, the other route you could take in a problem like this is at this point right here, I could have added that to the other side and had log x squared equals positive log 4. By moving that to the other side, I'm adding it. And now I have log base 10 equals log base 10, so x squared must equal 4. So that's a pretty good shortcut there. Could I do that with this problem? No, it's not equal to 0, and it is addition. It has to be something where I can get a positive log equals a positive log. Okay, now the directions here are telling us to actually use tables and graphs to solve these exponential, logarithmic equations and inequalities. So I have changed these notes a little bit. We're only solving exponential equations here. I am not using tables and graphs, but you can use the tables to find the solutions. I just thought it'd be good to do some extra practice. So when I look at this problem, I believe I could figure out that I could use a base of 2 here. And I'd have to mess with my numbers, but 2 to the 10th, there it is. 2 to the 10th is 1024. So if I see that, I can come in and change that. 2 to the 2x is equal to 2 to the 10th. My base is the same, so my powers are equal. So 2x equals 10, and there it is. X is equal to 5. Again, if I don't see that, I could have come in and taken the log of both sides. There we go, log of both sides. And then this would come out front as 2x times log 2 equals log 1024. And then I would leave that alone, divide by log 2, divide by log 2, and then I would have my 2x, or I could have divided by 2 log 2. And I have my 2x is approximately, and I'm just going to throw this in the calculator, log 1024, closing my parentheses, dividing by log 2, and I get 10. Well, that makes sense. And then divide by 2, and there we are again, x is 5. This is definitely the shortcut if it works out. Okay, looking at this, I have 3 logs here. Wow. So I could move this log over and have it set equal to 0, but I'm going to go ahead and write this as a single log. So this would be log of x divided by 2, and that is going to be equal to log 75. And I'm going back to what I called my common sense rules. These are both log base 10. So if the log is the same base, then that means that x over 2 must equal 75. And then I just have to multiply out the 2, and there's my answer. X is 150. And again, since this is base 10, I can plug it in and check it. Okay, last problem for you. I could come in and take the log of both sides, which gets a little bit sticky when I have powers on both sides, but we can do it. But I'm going to go ahead and change because I know that 2 squared is the same as 4. And I'm writing it in this particular way for a reason. I have 2 to the x, and I have 2 squared because I'm replacing the 4 with what it is equal to. And then I have to use my power property. So this is really 2 to the x equals 2, and then this multiplies, and that's what we don't want to miss. We don't want it to be 2x minus 1, it should be 2x minus 2. So if my bases are equal, then my powers are equal. And then I would subtract my 2x. I get negative x equals negative 2, and we end up with x equals 2. All right, so those are our extra notes on logarithmic equations and inequalities. Thanks for joining me.